we call neutralinos. These are the lightest, stable, supersymmetric particles that have been suggested. And these particles, in principle, could be discovered in the Large Hadron Collider, but the energy may not quite be sufficient to actually discover them. So we will have to wait and see. There are other candidates, but this, I would say, is the leading candidate for dark matter.
Thank you.
Any other questions?
I have one. Can you hear me?
Yes.
Okay. I have a question regarding the, first of all, I should announce that I am not a technician in any sense. I'm from the mathematics community as opposed to the scientific community. There are several things about our current interpretation, if I understand the interpretation correctly, that I don't understand. If I understand it correctly, something like 79 to 95% of our theory is not confirmed yet. Dark matter, dark energy. The Pioneer anomaly, has that been explained? And if there are stars and galaxies at the furthest extent, does that add further skepticism to the basic assumptions of our understanding of things? And I'm curious, I guess, whether or not anybody is looking at that basic assumption, which, if I understand it correctly, is all based on phase shift. So can you speak to some of that?
Yes. So first, let me take exception with your statement that things are not confirmed. Okay.
Okay.
We see the effects very, very clearly. I mean, there is no question that we see the gravitational effects of things like dark matter. There is no question now that the expansion of the universe is accelerating. So in that sense, these things are confirmed. Now, the question is, what is, for example, the nature of the particles that constitute dark matter, and what is the nature of this dark energy? Is it associated with the quantum energy of the vacuum, or is it some field that we have still not yet identified, and so on? So how are we progressing about this? And is anybody, you asked, is anybody thinking about other possibilities? So the answer is yes and yes. So in the case of dark matter, for example, there is one theory that is called TeVeS, stands for tensor vector scalar. It's a modification of our theory of gravity, which suggests that maybe there is no dark matter, but we need to change our theory of gravity in some particular fashion. This theory is just about at the point where it can make some predictions. The problem is that so far those predictions are not particularly distinguishable from predictions of dark matter. So it will be a while before we will be able to tell whether we need to change the theory in that case or not. Now, in the case of dark energy, there have been other types of alternative theories of gravity that say that maybe you can get acceleration without dark energy, in particular with gravity escaping into other dimensions that we don't perceive. Those theories, people have developed quite intricate models of those, but so far, in experiments that have to do with lunar ranging, and by the way, landing on the moon will allow to do somewhat better experiments on that, and experiments that have been done in the lab at the University of Washington, Seattle, which test the law of gravity, so far do not confirm those alternative theories. So at the moment, dark matter and dark energy look like our best candidates, and we certainly continue to work to try to find the nature of both of those components.
Do you have anything on the Pioneer?
On what?
On the Pioneer anomaly?
The Pioneer anomaly, some people suggest that some of these TeVeS theories, or sometimes the early version of that is called MOND, which is modified Newtonian dynamics, can also explain the Pioneer anomaly. But there have been more mundane solutions that have to do with radiation from the spacecraft and so on. So while we don't know for sure what the answer is, it's not that people are not looking at that.
Thank you very much.
Thank you, Dr.